This video, we're going to talk about power and changing a type 1 and a type 2 error. So at this point, you should have an understanding of what a type 1 error is, what a type 2 error is. So what happens in statistics with type 1 and type 2 errors is before we go into a hypothesis, you can talk about what a theoretical type 1 error is, what a theoretical type 2 error is, in the context of the problem. So perhaps when statisticians look at a study and they realize, a type 1 error, the consequence would be we spend more money than we need to, where a type 2 error would be we're potentially going to risk a lot of people's lives. So a type 1 and type 2 error, it's think of it like a scale, and of which way you can go. So if one means, hey, we might spend more money than we can or than we have as a consequence versus, hey, people could die. Statisticians can look at it and say, you know what, of those two consequences, the one that I want to make smaller is the fact that people can die. So they might increase the size of a type 1 error, spending more money than they need to, versus while diminishing the chance that people's lives are at risk. So you can look at a type 1 and type 2 error. There's a balance between the two, and you figure out, well, which one's worse? Which consequence is worse? And you balance it so that you diminish the consequence, but obviously it's going to increase the chance of the other type of error. So we're going to look at how can you change kind of the chance of a type 1 versus a type 2 error. The other thing I want to talk about is power, okay? So power is going to kind of tie all these things together. First off, if you just look at my graphic here, and we've looked at this graphic before when I talked about type 1 and type 2 errors, think of this line down the middle as a line that can move left and right, okay? So type 1 error and power are on one side and type 2 errors on the other. So as this line slides around, it's going to affect these two the same way, and type 2 is going to work in the opposite way. So let's talk about this thing called power that I haven't really dove into yet. So what power is, it's the ability to detect the alternative hypothesis. So if this is what we assume to be true, which is our null hypothesis is true, maybe our alternative, we think, instead of the distribution being centered here, our alternative, what we're trying to prove, maybe it's centered much, much further down here. So power is the ability to detect the alternative hypothesis. So if there's a claim that the average ACT score is a 22, and you're like, nah, I think it's higher. I think the average ACT at this school is a 22.1. You're not really arguing a huge big difference. So power would be like, well, instead of you saying the average ACT score is a 22, I might be arguing it's a 25, which is way over here. So it's the ability to detect that alternative hypothesis. So what I'm going to look at is three ways you can increase power. So as you change power, it's also going to change the type 1 error and the type 2 error. So as much as I'm talking about increasing or even decreasing power, if you're changing one of these, you're going to see how all three kind of interact. Okay, so how to increase power, how to increase the chance that you're going to detect an alternative hypothesis. Because if you have no chance at detecting an alternative hypothesis, you're wasting your time with a hypothesis test. If there's no chance that the alternative can even be found in your data set, then you're wasting your time. So how to increase power? The first way you can do that is increase alpha. So if you increase the size of a type 1 error, you're going to increase the size of power, okay? Here's how you can think about it. The chance of a type 1 error is this shaded region right here. The chance of power is all this non-shaded region under this distribution. And while I'm talking about it, this tiny shaded region over here is the chance of a type 2 error. So if you increase alpha, excuse me, think of it like this. This dashed line down the center, it can be moved one way or the other. Okay, so I redrew my graphs down here at the bottom. If I'm going to increase alpha, imagine my dashed line is right here. So I would have shaded right here my type 1 error. This entire space is my power, and the shaded over here is type 2. If you want to increase alpha, that means you need to increase the size of the shaded area. So maybe that dashed line moves a little bit this way. So if you increase alpha, this shaded space becomes much, much larger. By in part, the amount of space that is power just got much, much bigger as well. So if you increase alpha, this shaded area gets bigger, power gets bigger, but in hindsight, what happens to our type 2 air, beta, gets much, much smaller. So let's say I move that dashed line way over here, which is much, much further to the left than what I've had it in my earlier picture. The area under the curve for my type 1 just got bigger. So alpha got bigger, beta, my type 2 air, got much, much smaller, and the space that would be power got much, much bigger. So increasing alpha increases power. But if you increase alpha and power, you're decreasing beta. Okay, so one way to increase power is increase your alpha. So instead of doing an alpha of 0.05, maybe you're doing an alpha of 0.10. Second way you can increase your power is increase your sample size. So my drawings aren't perfect, but I'm just trying to still illustrate a basic point here. When you have a distribution, say this is like sample size of a sampling distribution with a sample size of 10. That's what the distribution looks like. As you increase sample size, so maybe I'm increasing my sample size to 100, what happens is your distribution is going to get not as wide. The area under center gets bigger, so it's much, much taller, and those tails really, really, really move in. So if you increase sample size, everything's going to pinch in here. So imagine that drawing that I had on the front of this piece of paper. It's the same type of drawing, but my two distributions are skinnier and taller, okay? So what happens is that type 1 air did just get a little bit smaller, type 2 still here, but the space that is power just got much, much bigger. So as you increase sample size, that space there in power gets much, much bigger there, okay? Much, much bigger. So increasing your sample size is going to pull those tails in a little bit and increase your power. So bigger sample size. And how it makes sense, well, what in this case, isn't your type 1 and type 2 errors both getting smaller? And in essence, yes, it's not a perfect drawing, but the more you know about a population, the more you know about a sample, the more you know about a population. So it's less chance you're going to make a mistake is the logic there. The third way you can affect power is test an alternative further from the null. And I did two kind of quick sketches here of that idea. If you would test an alternative hypothesis, so this is my null, this is my alternative. If you test a null hypothesis and alternative hypothesis that are really, really close to each other, there's going to be a ton of overlap. So if I got, say, an X bar that's centered right here, if your alternative hypothesis is very close to your null hypothesis, it's hard to tell which distribution does this X bar belong to, okay? It looks like it could definitely belong to this null, and it looks like it could definitely belong to this alternative. So first off, it's just a terrible idea to just test an alternative really close to the null. It's going to be hard to decipher which one is true. Additionally, that dashed line, this would be your type 1, this would be your type 2, and this is power. So the space that is on the right side of this dashed line is power is much, much smaller than my earlier drawings. Instead, if you test an alternative much, much further from the null, your power is going to get much, much bigger. So there's your type 1, there's your type 2, and there's your power. So the space under the curve there is much, much bigger for the power. So the three ways we can affect power is increasing our alpha, increasing our sample size, and test an alternative further from the null. You can again use those same ideas to kind of play around with other tricks here. You know, you could have questions of, all right, well, what if I increase the size of my type 2? What does that do for my type 1 error? What does that do for my error? Well, if you're increasing beta, yeah, it's going to slide to the right, so alpha decreases, power decreases as well. Stuff like that. So imagining this picture gets you through a lot of questions and thoughts around, well, would I increase power? How would I decrease type 2? How would I increase type 1? You can do all of those things. So when you're looking at a hypothetical statistical inference and you want to diminish a type 1 or type 2 error, you can do that. The other pieces, again, were increase in alpha, increase in sample size, and test an alternative further from the null. So that is power and changing type 1 and type 2 errors.